Hello and welcome to EE233. I'm your instructor, Gregory Myers. In this video, we're going to focus on an older version of our P5 modified. This particular version is going to focus on the physics demo. This video assumes a couple of things. Number one is that you have completed a version of P5 that you can then apply some of the principles to this P5 modified. This also assumes that you've watched the earlier fundamentals demo video focusing on the differences between passing, parallel arrays, and structures, as well as the setup videos for this project as well as your P5 project. So what we want to do is we want to take a look at one of the functions in this particular video. I'm going to focus on my projectile 1D version 4 modified. I'm also going to focus on the structure associated with it. You'll notice that my structure here, known as projectile underscore 1D underscore results, basically wraps around or contains fields that correspond to the values that were passed in our earlier projectile 1D version 4, the unmodified one that accepted parallel arrays. Fundamentally, what we're doing is we're just basically putting a nice little wrapper around all of our arguments and passing them then as a single argument by reference, which allows for us then to modify some of the fields inside of the structure. So real briefly, we'll take a look. You see you have your n, you have your y init, which is the initial height for projectile 1D problem. We have a time vector that once again is way too large. We're going to focus on static arrays for this example. It's going to be dictated by n max. N max is currently 100, whereas n is supposed to be the actual number of elements calculated that is going to be provided by our user. The idea is that the n should be include 2 or go from 2 up to n max, some value in between those, including 2 and n max. Same with our y time and our vy time. So at this point, basically, we're quite frankly wasting a little bit of memory, but we'll come back around to this. Instead, what we want to do is we want to focus on the ability now to pass an entire structure to a function. How do we manipulate that inside the function? So we're going to begin with by jumping straight to the function. You'll notice that I've already updated my comment block. I've already set up my results variable and initialized it to exit success. In other words, I'm pretty much ready to jump straight into the validation. And the first thing that we want to do is we want to go ahead and validate whether, in fact, we actually got past a valid example or a valid projectile 1D results structure. And we simply do that by checking to see if our example is equal to null. If it is equal to null, then basically what we've got is we have a problem. And so we can say printf error or null structure passed or null value passed. And the way we're going to do this particular project, it's unlikely that this is going to happen, but you want to go ahead and get into the habit of putting in this validation or this error checking. And then at this point, that we want to do is we simply say results are equal to exit failure. Now, assuming that we at least have a valid a valid structure being passed, or rather the address to a valid address to a structure being passed, then what we can do is we can dig into some of the fields in the structure and validate them, much like what we did when we were passing them as individual arguments. And so what I would encourage you to do is to go back and look at your P5 and look at some of the fields or some of the values, input arguments that we validated. For instance, on this particular one, we said that we wanted to have a positive y init. We also wanted to say that our n fell between 2 and n max, including 2 and n max. And so what we can do is we can simply go through each of these and validate them, much like we did in the earlier example. However, the difference is going to be we are going to have to reach into our example variable using the dash greater than, which allows for us to test the value associated with the element inside of a structure that has been passed by address. So what we're looking at now is we are going to check our y init. And if for some reason our y init that was passed was less than or equal to 0, in other words, isn't a scenario that we want to handle when we're dropping something off of a building, we're assuming a positive height, printf error, please provide positive height. And once again, you can bring some of this over from your P5. And then fundamentally, though, you're going to have exit failure. Continuing on with this, we want to validate then our N, and we do the same thing. And you'll notice that if I did decide to just use the dot notation and say, in this case, example.n, NetBeans will actually change this to the dash greater than, which will allow for us to access the value in N and not the address. We'll see later on how you would go ahead and check the address of a particular element inside of a structure. But in this case, we're looking at the value associated with that structure. So the N, if for some reason our N was less than 2, or N was greater than our N max. In either scenario, this is not what we want. And at this point, then we're going to have a printf. This says error, please provide an N from 2 to, and then %d, followed by a new line. And we simply use or take advantage of our constant. No matter how you do this, whatever the message looks like that you provide back to the user, we do want to go ahead and set exit failure. At this point, we should probably go ahead and validate that each one of our fields are valid structure, or excuse me, are valid arrays inside the structure, but we're going to assume for this example that we wouldn't have ran into this scenario. And so just a little comment here, you should consider also validating the other fields. And once again, this is just a good habit to get into. We're going to go ahead and jump into the calculations here so this video doesn't get too long, and that we're going to go ahead and mimic some of the steps that we took in the earlier example, and that we want to have our T delta. And then we also want to have our T final. And then additionally, we can provide then a Y final and a VY init. We're going to keep this one relatively straightforward in that we're going to have a VY initial, which is going to be equal to 0. In all of these cases here, we want to go ahead and set, we'll go ahead and set our VY initial equal to 0. And then let's go ahead and do some of our calculations here. We're going to have our T final. Our T final is just going to be much like we calculated before, the square root of -2 times our example. And then, of course, your first inclination is going to be to do dot our Y init. And once again, NetBeans is going to help us by changing that then to the value at that location in the structure. And then we simply divide this by our constant AY, which we brought over then from our P5. At this point, then you've got your T final. You also want to calculate your T delta. Your T delta is going to be the T init, or T final minus T init. And once again, this is probably a good variable for us to have for future expansion. We are not going to be covering it in this video. But then we want to simply initialize our T init to 0. And then you divide this, once again, just like in the earlier examples, by n minus 1. But the problem with it is that we don't have direct access to the n. Instead, what we want to do is we want to leverage the n that has been passed to us by virtue of our example structure. And if it helps you any, I would encourage you, at least in the beginning, to go ahead and use an extra set of parentheses around here so that you can sort of appreciate what's going on here. Some of the symbols may be confused with some of the signs here, but basically what we're doing is we're getting whatever the value of n is that's stored in the structure, and we're subtracting 1 to then provide then the segment length, or our t delta, when we have n data points. At this point, it's not going to look too much different from what we've done before. We're going to set up a for loop where we index from 0 up to, but not including then, our example n, whatever that value might be. And then we simply increment our index. That once again leads us to adding another variable here. We're sort of doing this a little bit backwards, but we're just adding these variables as we start to see them being necessary. We don't have to worry about initializing our index because we're using it inside of a for loop and not a while loop. And then at this point, what we can do is we can systematically go through each one of the parallel arrays that are being held in our structure, starting with our time. We use the index then to indicate which element in the parallel array that we wish to update. And we simply then take our t delta and multiply it by our index. And once again, this just leverages the fact that in C, we are using zero-based indexing. And so 0 times t delta means that your initial time is going to be 0. If you want to, what you can do is you can also go ahead and add on your t init. Once again, depends on how you are doing your time calculations as to whether or not you want to add this here or not. This is for a future video. It just allows for a little more flexibility in our project. And then we have example, and then we focus now on our y time, which is basically our height as a function of time. We look at the element associated with that index, and then what we're going to do is we're going to leverage the initial height, which is our y init. We're going to add to it whatever that vy init was, which does happen to be 0 here, times, and then our tendency is going to be to do time square brackets index. But once again, we can't use this by itself. We have to specify that it is the time array or time vector associated with our example structure. And then we add to this then our 1/2 at squared, which is going to be 0.5 times our a y times then whatever the value is for time. But once again, we want to prefix that by the structure name. And then we can specify then the location in that time vector. Now, in this case, it's going to be squared, so we can either multiply it again by itself or use the power function. It does not matter to me which one you do. Both will result in the same answer. Now, at this point, the only thing left to do is to focus on our vy time. Our vy time, once again, is also a parallel array, just like in our earlier version of our v4, except the difference is it is now part of this example structure. We want to, once again, add our vy init to it, plus ay times then the time square brackets index. And as I mentioned before, we'd like to do that, but we need to prefix it by the structure. So fundamentally, nothing really changed in our v4 modified, except for the fact that we have to now leverage or reach into the structure for the fields. And this basically just helps simplify the interface. In other words, simplify the function signature, but conceptually, it doesn't change much about our code. And so what I would encourage you to do at this point is just simply pause the video and then go back and compare it to your earlier example for P5, the V4, which was unmodified, or look back at the earlier video to see then the differences or the similarities between these two blocks of code. At this point, let's go ahead and build it just to make sure that we haven't made any mistakes, introduced any bugs. And then what we can do now is we can jump back up to our main. And as I mentioned before, what we're going to do is we're going to keep the same structure in our main. All the switches stay the same. We're still going to go ahead and collect the data from the user. In this case, we're focusing on our /1d/I. But the difference being then is we're going to take those values and we're going to actually insert them into our example structure, which means that in addition to our y_init, to accomplish this, what we want to do is we want to actually create a projectile1d results. And what I'm going to call this is, I'm going to call this a rather long name here, but just so we can distinguish between projectile_1d_example. Now, we can't just use the example variable by itself because we're going to use this for 3 different functions. So we have to distinguish. So effectively, we're going to have a projectile1d example and then examples for the other 2 functions as well. Now, just like any other data type, this is now declared, but it is uninitialized. In other words, most, if not all, of the values inside the structure will essentially be junk. And so we have to be careful about how we use the fields inside a structure if we have not yet initialized them. And so we're going to leave some of the error checking to the function, and we'll actually leave some of the additional error checking to a later video. But what we're going to do is blindly assume that the user has put in a valid y_init and a valid n. And then down here inside this branch of our if statement, we're simply going to take then the n that they have put in, and we're going to assign it to our structure. And so the n on the right represents the singular variable that was collected using the scanf, and the n on the left that's associated with the structure is simply then a field inside the structure. We do the same thing now with our y_init, and we simply take the y_init that was captured from the user. Now, do not get hung up on the fact that these variables are named the same. That's just to keep a consistent story going with this project. These 2 variables do, in fact, not have to share the same name. As a matter of fact, in a later video, we'll see how we can differ them just a little bit, how we can leverage that. Now, at this point, we are truly ready to go ahead and call our functions. So we say results are going to be equal to, and then projectile1d results, and we pass to it a singular variable, our projectile1d example. And at this point, then you're going to be inclined to go ahead and build this, and you're going to get a warning, and specifically an error, actually, not just a warning. But what we're going to do here is we're going to notice that we have to pass the structure rather by address. And so what we want to do is we want to pass then the address of our projectile1d example, because remember, our whole goal here is to do this by reference. And so if we build this one more time, we don't have any typos. We still have a typo here, though. Let's see what we've got. Let's see here, projectile results equal to, we have our results, projectile1d example, and projectile1d results. Let's make sure that we have our, oh, I'm sorry. Let's go back here one more time. I let my autocomplete do the work for me. Let's just start this line over so we don't confuse everybody. We'll say results are equal to, and then what we'll have is we'll leverage so it's not actually showing up here. So let's go ahead and do this the old-fashioned way. We'll say projectile_1d version 4. There we go. I let my autocomplete help me a little too much here. So I'm going to go through the mistake one more time so you can see the problem. There's our function. And then what we want to pass to it is our projectile1d example. And now if we build this, we should get the error that I was expecting. And then you'll see that we are trying to pass it a structure, but not the address of the structure. And so what we want to do is we simply change this then to the address of our projectile 1D example structure. All right, so let's go ahead and build this. Now it works correctly. And I guess a little minor warning here is don't let your autocomplete get the best of you. At this point, just like in our earlier examples, we want to check to see if our results were equal to exit success, because there's no point printing out a table if we weren't actually able to calculate anything. And then under the else, we simply have a printf that says error, failed to run function. And you can once again improve those error messages as you go along. But now what we want to do is we want to look back to our P5 and we want to think about what does it mean to print out those results. Well, we want to have a combination of things. Number one is in our P5 sample, you saw that we were going to print out a nice little table here. We'll continue that pattern, but we also want to print out a CSV file. And in this case, for this particular project, it's going to be a 4-column CSV file with the index, the time, the y or the height, and then the velocity v_y. And so we're going to be doing a combination of things. We'll start off with the table first. And what we're going to do is just print out a nice little table of our results. And we do this under the true branch of our if statement here. We have printf of the column headers. Create a nice border for your table that you can probably consider reusing. And then inside, then you just go through each one of the values. And I'm going to recommend to you just to go ahead and use the %8.4f for this particular example. We'll do our y init, which was in feet, %8.4f followed by a new line. And now what you want to do is you want to plug in the value for y init, but instead of using the one that's associated with that singular variable, let's prove to ourselves that we've actually got this working correctly, and that what you can do is you can actually leverage your projectile structure, your projectile 1D example structure. And now you'll notice that I can get away with using the dot notation, because outside the function, I'm not dealing with the address of the structure, I'm dealing with the structure itself. Continuing on with this, we probably also want to capture or print out to the user the n or number of elements that they requested. Once again, just to confirm that we actually understood or collected the data correctly. And so we have projectile 1D example dot n. And at this point, hopefully you're starting to see how you would go about completing then the rest of the table. So what we'll do is we'll follow the sample on the right-hand side of the screen with our y final. Our y final is, of course, also going to be in feet, %8.4f. We do not have a nice convenient variable for this. Instead, what we're going to do is we're going to leverage then our y time array. And remember that we have n number of elements in there. So n-1 represents the next to the, well, let me rephrase that real quick. n-1 represents the last valid element in the array. So n is the number of valid elements in the array. n-1 is the index of that element. And we could, of course, use n because we do have it as a local variable, but let's try to get away from that. What we can actually do is we can actually nest the calls here. So we can say projectile_1d.example.n-1, and we'll actually use then the value that's stored in the structure. Now, continuing on with this, we can do a printf for our vy init. This, of course, is going to be in feet per second. We'll go ahead and keep the same 8.4f pattern. once again, this is part of the structure. So we're going to leverage now our VY time. And for this one, what we're going to do is we're going to use the 0th element. This once again just validates that we have correctly assigned those values inside of our function. We could, of course, have used the y_init variable up here, or the vy_init, sorry, vy_init, not our y_init. We did use the y_init here. Matter of fact, why don't we go ahead and change this just to verify that we did do this correctly. And then the same thing for our VY final. That is going to be the n-1 element, which once again, we could leverage the n, but we might as well go ahead and leverage the n associated with the structure. And then projectile underscore 1D underscore example dot n minus 1. And at this point, we should have all of the fields that we had wanted to print out to the user. We have our y_init, y final. Actually, we probably should go ahead and throw our time in there. So printf, we'll do our t_init, which is going to be in seconds. That's also going to be %8.4f. And then hopefully you can start to see the pattern now. As a matter of fact, I'm actually going to do a little bit of convenient copying and pasting here, in that we're not going to be doing the y_time for this one. We're actually just going to be using the time. And then same trick for our t final. Of course, what we're going to do here is we're going to once again leverage our projectile underscore 1D underscore example dot n and then minus 1. And that once again gets us the last valid element in our array. Before we go any further, let's go ahead and build this. Remember that we have already verified that our switches work correctly when we were working with our P5. And so we've just simply brought those over. So I'm going to go ahead and CD from my P5 over to our P5 modified dist debug and then min_gw directory. You'll see there is my P5 modified example. And then we're going to go ahead and run our /1d/i, which should prompt us for the height and the number of points that we wish to calculate. And you'll see, other than a little bit of a formatting issue that we probably should reconsider, then you have our n equals to 11, our t_init goes from 0 to 2.49 for t final. Our y_init starts off at 100, our y final is 0. We have a little bit of round off error there. And then we have our vy_init, which was 0, and our vy final, which is essentially the velocity right before impact, then is negative 80.2496 feet per second. So at this point, then the only thing that we have left to do is to go through and write our results to a CSV file. And so in order to do that, the first thing that we want to go ahead and do is we want to go ahead and declare then a pointer to an output file. We should have all of the variables that we need to accomplish this. And so what we'll do here is we will go ahead and use that variable for the output file pointer, and we'll do fopen. And I've allowed for you in this particular project to go ahead and hard code in the file name. So it's going to be projectile underscore 1D underscore v4. There's no reason to change the output file name for this project because essentially the format's going to be identical to your P5. We're going to open this for writing. And the first thing that you want to do is you want to check to see that your output is not equal to null. In other words, the output file pointer is not equal to null, indicating that we have been able to successfully open the file. Else, we simply have a printf that says error, failed to open output file. Now, at this point, then we are simply back to what we had done earlier, where we build a for loop that starts off at index equals 0, going to index up to, our n, but not including our n. Once again, we could leverage our n variable Instead, what we want to do is we want to leverage the n associated with the structure. And then we once again want to increment our index. So hopefully at this point, you're starting to see the pattern of using the fields in the structure as opposed to the individual elements or the individual variables. At this point, then, we can simply very carefully craft our fprintf statement using our output file pointer. And we want to make sure and match a logical pattern for the format spec, starting with a %d for the index, which was the first column, the %8.4f, which we will keep consistent then for this project, but might change in the future. And so we're going to have 3% 8.4fs followed by a new line. In that first %d goes the index. In the %8.4f, what we would like to put in there is going to be the time square brackets index. But remember that we don't have a time vector by itself. What we want to do is simply prefix that with our physics or projectile rather, underscore 1D underscore example. And that gets us our first %8.4f. We can then do the same thing now with the other fields. So projectile underscore 1D underscore example dot, and now we want to go ahead and do our y as a function of time square brackets index. And if it helps, because this is starting to get a little long, I'm going to stack these. And then we have our projectile underscore 1D underscore example dot vy time, which is then the last column square brackets index. And then the last step, of course, is whenever you open a file, you want to make sure you close the file just so that you don't have any problems in the future. And one little minor change I'm going to make here, I'm just going to put each one of the values that go in as placeholders on a separate line so that hopefully you can see how each of the pieces go into the output file, this time, though, using a structure. I'm going to go ahead and build it. I'm going to come back to the command line one more time. I'm going to run it. Initial height of 100, number of data points 11. Now when we do a dir, you should see a projectile underscore 1D version 4.csv. That looks very promising. And sure enough, here you have a 4-column CSV file with 11 rows, with the first column being the index, the second one being the time, the third being the height associated with a given time, and then the fourth being the velocity associated with that time. Last thing that we need to do for this particular example is simply very carefully go through and copy all of the code that we would have otherwise had in the /i branch down to our /p branch. And so we'll have to be very careful to make sure and get all of our if statements all the way and up to where we have assigned then the values to the structure that in this case now we collected from arguments from the command line. Now, we are in fact have a significant amount of duplicate code here. In a later video, I'll show you how to tweak that a little bit. I've alluded to it in the setup video. That's where you want to have these helper functions. The helper functions serve the purpose then of removing the duplicate code and putting it in one location. But for right now, a little bit of duplicate code is not the end of the world. We can go ahead and build it one more time. We can come out to our command window. We'll change our /i to p, and we'll provide the arguments from the command line. This time I'm going to provide a different number of argument or a different value for the second argument. You can see here that my n is now 21. My values haven't really changed any, but effectively what I have is a little better resolution on the process or the values for the ball falling. And so you can see here, basically, I just have a smaller delta t. So Hopefully you found this video useful. I would encourage you to, before you start looking at the other videos on the 2D and Beam, that you go ahead and give the other ones a shot by yourself. The next videos are going to be very short because I'm just going to simply explain to you what the difference is between the projectile 2D version 4 and the version 4 modified, likewise with the Beam. So if anything, you should feel pretty comfortable in being able to do this by yourself. As always, if you have any questions, comments, or concerns, don't hesitate to reach out to me. And thank you for watching.